All right, in this third video of our first unit, we're going to be talking about critical points. We've already seen some critical points in the forms of local maximums and minimums. We're going to be adding two more points to our list of critical points, which are going to be the x and y intercepts. Another word for x-intercepts are the zeros of the graph. So when we talk about zeros of the graph, we're talking about where the function crosses the x-axis, otherwise known as x-intercepts. So, taking a look at a couple of graphs, on the graph on the left-hand side, if we look at where our graph crosses the x-axis, there are a total of 1, 2, 3 points where our graph crosses the x-axis. Those points are -2, 0, +1, 0, and +3, 0. Notice that we also call them zeros because the y values of each of them are 0. So pretty quick and easy with these. On number 2, we have 2 points where our graph crosses the x-axis. The first is -1, 0. The second is 6, 0. Two other types of critical points are called relative maximums and relative minimums. These are just another name for something we saw in the previous lesson, which was a local maximum and a local minimum. So just to do some practice with that, let's go ahead and identify what those points are on our graphs for number 3 and number 4. So number 3, let's first look for any relative maximums. So we'll look for anywhere our graph switches from increasing to decreasing, or where it looks like the top of a hill. And taking a look at this point that I've circled, we are switching from increasing to decreasing. That would make this point a local maximum. So our maximum would be at that point, -1.155 and -2.921. So local minimums we'd look for, are there any points that look like the bottom of a hill, like this point does, where our graph switches from decreasing to increasing. And in fact, we do have one of those points. On this graph, that is the point 1.155, comma -9.079. All right, let's take a look at number 4. So number 4, relative maximums. We're looking for anything that looks like the top of a hill. And here we've got a point that looks like that. It does switch from increasing to decreasing, so that would be a local maximum at 0, -6. For minimums, we're looking again for any points that look like they're at the bottom of a hill. We've got 2 of those points. They both switch from decreasing to increasing, so we know that those are both relative minimums. So listing off those points, -1.414, comma -10. The other point, 1.414, and +10. Okay, a couple of other points to mention to you guys, and then we'll be done with this lesson, are x and y intercepts. So x-intercepts we already looked at. Those were the zeros of a function, so it's where a function crosses the x-axis. X-intercepts, there can be multiple. Y-intercept is where a graph crosses the y-axis. Notice that here there's only one, because if you think about it, if there were more than one, it wouldn't pass the vertical line test. For example, on number 5, if you had 2 points that cross through your y-axis, then if you drew a vertical line, it's going to go through both of those points, and that's no longer a function. That's not a problem with x-intercepts. We don't have to worry about that with those. So on each of these graphs, let's identify the x and y intercepts. So number 5, where our graph crosses the x-axis, there are 2 points where that happens. The first is 2, 0. The second is 5, 0. And again, there's only one point where you cross your y-axis. Your y-intercept is at that point 0, 10. On number 6, it looks like we also have a couple of x-intercepts. The first is at -4, 0. The second, -1, 0. And for y-intercept, again, we've only got one of those. This one happens to be at 0, -4. Lastly, number 7. So x-axis, we've only got one point that crosses the x-axis, That is the point 2, 0, and 0, -8 is the only point where it crosses the y-axis. So that would be your y-intercept. Okay, I believe that's all I've got for you guys in this particular lesson. In the next lesson, we will talk about end behavior, even and odd functions, and symmetry. Until then, have a good rest of your day.